Swayam Prabha. Digital India. Educated India.
Hello friends, welcome back to the lecture series of BSc with Chemistry, Physical Chemistry Paper 4. From this lecture, we are starting with Module 3. This is particularly lecture 1 of Module 3. From this lecture, we are going to see electrical and magnetic properties of atoms and molecules. Now friends, we know that there are various methods used for the study of molecular structure. Now, these methods may be broadly classified into, say, physical and spectroscopic types. Methods which are based upon the study of physical properties of the substance, say, we can call it as, say, physical properties like molar refraction, optical activity, and dipole moment. They are of physical origin. And spectroscopic methods, they can be of, say, rotational and vibrational spectroscopy, UV visible spectroscopy, Raman spectroscopy, that we have seen earlier also in some other lecture series. Now, these spectroscopic methods, they have discussed in our one of the previous course lectures. This was particularly the paper of quantum mechanics and molecular spectroscopy. Now, in this particular paper, what we will see, we shall take up the brief discussion of, say, important physical property of dipole moment for my molecular structure determination. And for determination of, say, dipole moment, let us first see what are, it is very important to see the polar and non-polar molecules, what we call it as a polar molecule and what we call it as a non-polar molecule. Now, whenever a covalent bond is formed, we all know that covalent bond is formed by the mutual sharing of electrons. Now, this sharing is between two atoms. So, if the two atoms are identical, say for example, we take an example of hydrogen or chlorine or any of such kind, in such types of molecules, the shared pair of electron is attracted equally by the both atoms, and therefore it remains exactly in the center of the two atoms. Okay, you can see here, correct? Now, because of this, there is neither of the two atoms in such molecular positions, they acquire positive or negative charge, isn't it? I mean, no atom will be getting positive charge and no atom will be getting negative charge. And therefore, the bond which forms in such cases between such two identical atoms is called as non-polar covalent bond. Okay. And the molecule as a whole is called as non-polar molecule. Now, on the other hand, if I take the other example, say if two atoms are dissimilar, say this kind of molecule, say HCl. Okay. Now, in this HCl molecule, the chlorine atom is more electronegative, isn't it? So, this more electronegative atom, because of its presence, the electron pair is more attracted towards the chlorine atom instead of going into hydrogen atom. So it will be, the electron pair will be going to more electronegative atom, that is chlorine atom. And because of that, the chlorine end of the molecule acquires a slight negative charge, which we called as minus delta. And while that of the other molecule, it acquires the partial positive charge, that is plus delta. And therefore, because of this partial charge development, there is a formation of dipole, isn't it? And therefore, the bond which forms because of this between the two dissimilar atoms having, say, slightly different electronegativities is called as polar covalent bond. And such kind of molecules, they are called as polar molecules. And you can see the situation which is shown over here in HCl molecule, isn't it? Now, because of this a dipole moment is developed, and this dipole moment is denoted by letter mu. Okay, so let us now see here what is dipole moment. Now we know that the basic electrical property of a molecule is its dipole moment, which helps in understanding the relative location of various bonds in the molecule. And the study of a substance in a magnetic field will help us in knowing whether this substance is paramagnetic or diamagnetic. Now, what is paramagnetism? So, let us say paramagnetism in a molecule, whatever we consider, is due to the presence of one or more than one unpaired electron. Whereas, on the other hand, in diamagnetism, no such unpaired electron is present. This is the basic difference. And therefore, this helps understanding the electronic configuration of atoms and molecules. And this is what exactly we are going to discuss in this particular module 3. This is what is called as physical property study of dipole moment. Now, the extent of polarity or say polarization of a molecule is expressed in terms of dipole moment. And the dipole moment of polar diatomic molecule basically is the product of say magnitude of charge on each end of molecule and the distance between the centers of their nuclei. Okay, that means it is a bond length of this particular molecule. Okay, in general what I want to say is, for a polar diatomic molecule say of AB type, this type, say in which I have this B as more electronegative atom than this A, and if I say this plus Q is the charge on atom A and minus Q is the charge on atom B, and let L be the length, bond length of this AB. Okay, this is a bond length of this molecule. In such case, the dipole moment mu of the molecule AB is given by this mu is equal to Q into L. Now remember that this mu is a vector quantity. It has both the magnitude as well as direction. And therefore, it is represented by an arrow which is pointing from the positive end to negative end of the molecule. Many a times it is represented as a bold face mu, which indicates that it is a vector quantity. Okay. So obviously, if the molecule is non-polar, my Q must be equal to 0. And therefore, in that case, my dipole moment must be equal to 0. Okay. Let us look at its units. In CGS units, in CGS systems, the electronic charge is expressed usually in electrostatic unit of charge, which we call it as ESU, and the bond length we usually measure in centimeters. And therefore, the dipole moment is expressed in ESU centimeters. Okay. So if the charge is equal to the charge on electron, that is 4.8 into 10 to the power minus 10 ESU, and the bond length is 10 to the power minus 8 centimeter, then the dipole moment will be given by 4.8 into 10 to the power minus 18 ESU centimeter. Okay. Now, herein you can see that electronic charge is of the order of 10 to the power minus 10 ESU, that is electrostatic unit of charge, and the bond length is of the order of 10 to the power minus 8 centimeter. So every time the factor of 10 to the power minus 18 will be generally appearing into the value of dipole moment. Okay. So this quantity of 10 to the power minus 18 is called as a dBA unit, and which is denoted by D. and therefore 1 dB is equal to 10 to the power minus 18 ESU centimeter. Okay, so in such case, in CGS unit, the dipole moment will be given by 4.8 D, that is D by unit. Got the point? Similarly, I can find out the SI unit. Okay, in SI unit, if I say the electronic charge is expressed in terms of coulomb, okay, that is the charge of one electron is 1.602 into 10 to the power minus 19 coulomb, and the bond length is in meter, that is 10 to the power minus 10 meters, and therefore the dipole moment is expressed in terms of coulomb meter. Okay, that is 1.602 into 10 to the power minus 29 coulomb meter. Now I know that this mu is equal to 4.8 D, and in SI unit this is 1.602 into 10 to the power minus 29 coulomb meter. So if I would like to find out the relation between 1 dB and coulomb meter, it would be simply 4.8 D is equal to 1.602 into 10 to the power minus 29 coulomb meter. That means 1 dB is equal to this particular quantity will be divided by 4.8, so it will be 3.336 into 10 to the power minus 30 coulomb meter approximately. And therefore in SI unit 1 dB is equal to 3.336 into 10 to the power minus 30 coulomb meters. Now basically, while studying the dipole moment, polarization plays a vital role. Let us understand what it is. Now molecules, whether we consider as a polar molecule or non-polar molecule, they are electrical in nature. And why they are electrical in nature? Due to the presence of positively charged nuclei and negatively charged electrons. Now the molecules are neutral because their net charge is zero. So if we consider first the case of non-polar molecule, in case of non-polar molecule, the center of positive and negative charges coincides. Look at this figure. Just a moment. Let it complete. You look at this. Okay. So when it is at center, both the charges, the molecule is non-polar. However, when such molecule is placed in an electric field, you can see the shaded color is represented by the presence of electric field. Okay. So whenever such molecule is placed in electric field, there is a displacement of electrical centers. You can see here, there is a displacement of electrical centers. Say, you can see it will go to the respective, this positive will go to this negative electron and this negative will go to this positive. Okay. So the center of charges, they shifts towards the one end due to the attraction between the oppositely charged poles of the molecules and electrical plates. Now due to this, a dipole is induced in the molecule, and this displacement creates a distortion of positive and negative charge in the molecule in presence of applied electrical field, and this is called as distortion polarization. This is called as distortion polarization of the molecule. Now this dipole is temporary and the molecule remains polarized as long as the electric field is applied, but it goes back to the original state as soon as the electric field is switched off. That is why this type of polarization is also called as induced polarization, and the electric dipole formed is called as induced dipole. And also the dipole moment of induced dipole is called as induced dipole moment, which is represented as mu I. Okay, look at this equation number 1. Now evidently the value of mu I depends upon the nature of molecule, which is quite obvious, and the strength of the applied electric field. Okay, say if I apply the electric field of say E, So it will be depending on this particular E of the fashion of this type. Mu I is equal to alpha into E. Now this alpha is the constant of proportionality, and it is called as polarizability of a given molecule. Now this polarizability, it is a measure of easiness with which a molecule can be polarized. So by definition, if you look at it, this alpha, that is polarizability, is equal to the induced dipole moment generated by a unit strength of an electrostatic field. If this is equal to 1, alpha is equal to mu I in such case. Okay, and therefore the definition of alpha is equal to the this alpha, which is equal to induced dipole moment, which can be generated by a unit strength of the electrostatic field. Now there are different types of polarizabilities, say electronic polarization, atomic polarization, orientation polarization. So what is called as electronic polarization? Electronic polarization is the electronic cloud of molecule when it is distorted towards the positive end of the electrostatic field. It is called as electronic polarization, and the polarizability is represented as electronic polarizability, that is alpha E. In case of atomic polarization, the nuclei or atoms, they are distorted towards the negative end of the field, and the polarizability is represented as this alpha A, that is atomic polarizability. And in case of orientation polarizability or orientation polarization, it is operative only when the molecule carries a permanent dipole moment. That is, the electrostatic field tends to orient the molecular dipoles along the field direction, and it is usually represented by alpha 0. And therefore the total polarizability, if you look at it, look at equation number 3, it is the sum of, or the algebraic sum of, the three polarizability, that is electronic polarizability plus atomic polarizability plus orientation polarizability. Now there's the electronic polarizability and atomic polarizability. They are taken together, they refer to the distortion polarization or distortion polarizability, that is usually represented as alpha D. And therefore this alpha D is equal to alpha E plus alpha A, that is electronic polarizability plus atomic polarizability. Okay, now if you look at the unit of polarizability, say alpha, which is equal to mu I induced dipole moment upon the field strength, that is E. So in CGOS unit, if I would like to find out the unit of polarizability, my alpha is equal to mu I upon E. The unit of alpha, unit of mu I is electrostatic charge of unit, electrostatic unit of charge, that is ESU centimeter, and field strength is ESU centimeter square per centimeter square. So it will be becoming centimeter cube. So you can see that the unit of polarizability in CGS system is nothing but the unit of volume. However, if you try to look at it in SI units, we have this polarizability is equal to mu I upon E. So now in SI unit, this induced dipole moment is given by coulomb meter, unit is coulomb meter, and this field is Newton per coulomb. So the overall unit is coulomb square meter per Newton. However, in SI system, this polarizability is represented by alpha upon 4 pi epsilon 0, where epsilon 0 is the permittivity of the medium. Now it has a unit of volume. How? Because this alpha is coulomb square meter per Newton, and 4 pi epsilon 0 is coulomb square per Newton per meter square. So it is giving you meter cube. So it has a unit of volume, isn't it? And therefore in SI units also it has got the unit of volume. Now this is the most important part herein in this particular discussion, the Clausius-Mosotti equation. This particular equation, it relates the distortion polarizability of the molecule with the dielectric constant of the substance, which is very important to study. Now the required relationship is derived from the experimental aspects. Let us have a look at it. Suppose that several molecules of a substance in the solid, liquid or gaseous states, they are introduced in the space. Now this space is between the plates of a condenser, which is charged by applying a constant electrostatic field, and this such substance is called a dielectric and is assumed to be an insulator. What the assumption? Now the charges on the condenser plate are partially compensated by the induced charges on the boundary of the dielectric. You can see at the figure. Look at the charge of this plate, look at the charge of this plate, and look at the charge on this molecules. Okay. Now the electric field strength in the dielectric is therefore reduced to a value, say E, from its original value E0 in vacuum. These two quantities, they are related to each other, say by this particular relation. E0 is equal to E plus 4 pi P. Now this P is the dielectric polarization, isn't it? And this dielectric polarization is induced dipole moment per unit volume of the dielectric, which is given by this particular expression. You can see over here. So now you must be able to relate that this is induced dipole moment. So P is equal to N into mu I, isn't it? And therefore, this induced dipole moment per unit volume is justified. Okay. This N, particularly in this equation 6, is the number of molecules per unit volume of the dielectric. Okay, you can see over here. So we can further write down this particular expression of 7, equation 7, that is E0 upon E. So if I would like to take this expression 1 plus 4 pi P upon E, so I can rearrange this expression, and if I substitute the relation of P from equation number 6, so I get this particular expression, that is 1 plus 4 pi N mu I upon E, isn't it? And from this particular expression I can write down this epsilon r, which is equal to 1 plus 4 pi N into alpha D. So from this particular, if you look at it, this is particularly the dielectric constant or relative permittivity, that is epsilon r, and this alpha D is equal to mu I upon E. So mu I upon E, instead of this I am substituting alpha D, that is distortion polarizability. So I can substitute this value over here, and therefore I get this particular equation 8. Now in this particular equation 8, we find the generation of dielectric constant, or say relative permittivity, which is epsilon r. Now this relative permittivity can be measured experimentally by taking the ratio of capacitance of the condenser with the medium and the vacuum respectively, as the dielectric between the plates, that is epsilon r is equal to C upon C0 from experimental measurements. Okay. Now suppose that 1 mole of a substance of molar volume Vm, say Vm, and density rho and the molar mass M, capital M, is used as dielectric between plates, then we can have particular this expression. Is it okay? Isn't it? So we can have this particular type of expression with this assumption. Now in this particular expression, this Na is the Avogadro number. Now from equation 8 and equation 10, we can get this particular relation. Epsilon r minus 1 into m upon rho is equal to 4 pi Na into alpha d. Isn't it? I have just substituted the value of n over there. isn't it? Now, since my alpha D is a molecular property and it is independent of density of medium, and therefore it can be concluded that this quantity, that is epsilon r minus 1 upon the rho, is independent of the density of medium, isn't it? And therefore the distortion polarizability is constant for a substance. Now with this particular equation 11, it is holding good for gases at very low pressures. Why? Because when the interaction of dipole moments between the neighboring molecule is negligible or negligibly small, it is applicable. And since the in such cases the basic reason is the molecules are far apart from each other. On the contrary, if I take the condition at high pressures and for condensed phase like a solids or liquids, this relation does not hold good. Now this is so because herein the interactions between induced moments have to be taken into consideration. Now Clausius and Mosotti, taking into consideration these interactions for condensed phases, they introduced the relation of this type. Look at it, isn't it? So molar polarization is equal to epsilon r minus 1 upon epsilon r plus 2 Vm is equal to 4 pi by 3 Na into alpha d. This particular relation is called as Clausius-Mosotti equation, and this is the generation of molar polarization. This is very important term, molar polarization, and this particular expression is called as Clausius-Mosotti equation. Now in SI system, the Clausius-Mosotti equation is written as this particular part. If I change this particular part for pi by 3, so it gives me Na upon 3 epsilon 0 into alpha d. Rest of part remains. So equation 13 is particularly the Clausius equation in terms of SI systems. Now herein the distortion polarizability is a characteristic constant of a molecule, and therefore the molar and therefore the molar polarization Pm, if I consider this particularly equation number 12, according to this particular part of equation 12, it should be a constant independent of density or a temperature. Now this has been verified experimentally for nonpolar molecule such as say hydrogen, carbon dioxide, methane, CCl4, etc. Because these molecules, they are nonpolar. These molecules, they do not have permanent dipole moment, and therefore the Clausius-Mosotti equation is not obeyed by polar molecules such as HCl, H2O, ammonia, etc., which possesses the permanent dipole moment, isn't it? So friends, in this particular first lecture, what we have seen, we have gained the idea of dipole moment. We have seen the concept of polarization. We have also seen the types of polarization. We have seen the electronic polarizability, atomic polarizability, orientation polarizability, distortion polarizability. We have also seen the units of dipole moment and polarization. We have seen the CGS and SI systems of units. And we have also seen the generation of Clausius-Mosotti equation for molar polarization. So we have seen the generation of molar polarization, and the particular equation is known as Clausius-Mosotti equation, wherein we have seen that the Clausius-Mosotti equation is found to be applicable only for nonpolar molecule which do not possesses a dipole moment, say for example hydrogen or methane or carbon dioxide or CCl4, such kind of molecules. The for molecules like HCl CH3Cl, H2O, NH3, that is ammonia, etc., wherein we have got the permanent dipole moment, the said Clausius-Mosotti equation, it fails very badly. And moreover, not only that, the it fails, but the molar polarization of such molecules, it cannot be determined with this Clausius-Mosotti equation, because uh, the polarization determined of such polar molecules, they are dependent of temperature. And basically, the reason why Clausius-Mosotti equation is not applied to the polar molecule, it was particularly studied by Debye. So in our next following lecture, we will study the Debye equation. We'll stop here in this lecture, friends. Thank you.